We've got a diagram drawn up on the board here of 3 pieces of metal. We're going to use these 3 different diagrams of pieces of metal or any other material that can undergo the photoelectric effect. Usually when we talk about the photoelectric effect, we talk about metal. It doesn't have to be, but no, when I say that, right, a metal surface, I'm talking about any surface that can eject an electron when light strikes it. I've got 3 pieces of metal up here, and in each of these 3 pieces of metal, there are electrons. We'll draw 2, but of course there's way more than 2, right? There's almost an infinite number of them. We're going to, in each of these 3 diagrams, shine light on these electrons, on these metals. The first one that I'm going to do is red. We have a photon. Remember, a photon is a particle of light. What's the technical definition for a photon? The real definition? We think of it as a particle of light, right? But what's the real definition? Remember that? We said it was, what is it? A quantum of energy. Yeah, a quantum of electromagnetic energy. So we have a photon here, a particle of light, a quantum of electromagnetic energy. And that photon is shining upon this metal, and it hits an electron. If we say that the frequency of this photon is less than, remember this term from yesterday, the threshold frequency? What's that again? Yeah. Yeah, good. The minimum EMR frequency necessary to eject an electron. This is the frequency that we have of the light. This is the frequency that we need in order to cause an electron to be ejected. So we're saying here, in this situation, what we have is lower than what we need. What happens when the frequency of this red light is lower than the frequency that we need? What happens? Nothing. Yeah, nothing happens. Now, what happens if I increase the number of photons? If I increase the number of photons, I could do that in really 2 ways, right? If I have a flashlight that emits 1 photon every second, if I have 2 flashlights, that's going to double the number of photons, right? It's going to double the intensity of the EMR. So if I do another one, that could be 2 flashlights. Double the number of photons, double the intensity. Or it could be use the same flashlight, shine it for a longer period of time, right? Twice as long. Doesn't really matter. It's twice the number of photons. Got it? What's that going to do to these electrons that are in this metallic or whatever other surface? Nothing. Okay? What we have is less than what we need. So it doesn't matter how many we have. It doesn't matter how long it shines upon it. If each one of them is less, each one that we have is less than what we need, then nothing's going to happen ever. Got it? All right, let's increase the frequency of our EMR right now. Let's use green. So now we've got a green light photon here, which green light is higher frequency than red light, right? Take a look at the poster over here. You can see red light, low frequency, green light, higher frequency. Roy J. Biv. We shine a green light photon, which we're going to say has a frequency that is above the threshold frequency. Frequency we have, frequency that we need, the minimum frequency necessary, the frequency we need to eject an electron. Shine that on this metallic surface or whatever other surface it is. What happens to an electron now? The electron gets ejected, right? Now, when that electron gets ejected, here, it has energy, right? What type of energy does this electron have? Right. So we get an electron ejected, and it has a certain amount of kinetic energy. What if I take this 1 photon flashlight? By the way, if you had a single photon, would you ever see that? No, it takes way more than a single photon to see it. But it's still visible light. It's just too small intensity visible light to actually notice. Okay, we're just simplifying it by talking about single-digit photons here. If you take another photon, double the number of photons, either by having 2 of those single photon flashlights, or by taking your 1 single photon flashlight and shining it for twice as long. Doesn't really matter. Increase the intensity, increase the length of exposure. Doesn't really matter. We're doubling the number of photons. If we do that, what's going to happen? Yeah, we're going to get another electron ejected, right? And that electron that's ejected is going to have kinetic energy, just like the first one. In fact, it is always, in this situation, a 1-to-1 ratio. If we take one photon and it's above the frequency that we have is above the frequency that we need, then you will get one electron ejected. If you take 32,112 photons above the threshold frequency, how many electrons are you going to get ejected? 32,112. Okay, and they're all going to have more or less the same kinetic energy there. Does that make some sense? When you're below the threshold frequency, nothing happens. That would be a 1-to-0 ratio. Nothing happens ever. But when you're above the threshold frequency, it's a 1-to-1 ratio. 1 photon, 1 electron, 10 photons, 10 electrons. What if I increase the frequency even further? This time we have blue light. This time the frequency is quite a bit bigger than the threshold frequency. The frequency that we have is way bigger than the frequency that we need. So there's our particle of light, our quantum of electromagnetic energy. Okay, we're shining that photon on this metal or whatever. What's going to happen? We're going to get an electron ejected, right? What's the difference between this electron now that's ejected, though, and the electron that was ejected with green light? It's going to be more energetic. Yes, let's label it this way. More energetic. Why is it more energetic? Like, look at the equation. Look at the equation that describes the energy of a photon. E is equal to h times f. If the frequency is way higher than it was before, then the energy of the photon is way higher. That's Einstein's big thing, right? The energy of a photon is h times f. The frequency is way higher, then the energy of the photon will be way higher. If the energy of the photon that strikes this is way higher, well, then that leaves a lot more energy for the electron, left for the electron, right? If you take a hammer and hit a piece of ice, then you can cause that ice to break, and you can cause pieces of ice to go flying, right? If you hit that ice with a hammer and with a lot more energy, so you crack it with a bigger hammer and a hammer that's moving faster, then the pieces of ice that fly off are going to be moving off a lot faster because they were given more energy to begin with. Same deal here. Okay? This blue photon has more energy than the green. Green was enough, but blue is way more than enough. That gives a lot of extra energy to the ejected electron, or the photoelectron. And you can see the way I have it represented here, more kinetic energy, more speed, moving faster because it's got more kinetic energy. Let's take a second photon. So we take our little photon flashlight, we shine 2 of them, or we shine the one flashlight for twice as long, and we end up getting 2 photons, double the photons. Strikes this, what happens? We get another electron ejected? Sure we do. And that second electron that's ejected is also going to be more energetic and therefore moving faster. So you got to understand what's going on here. Red, in this situation, below the threshold, red isn't always below the threshold frequency, right? But in this case, it is. Each metal is different. For this metal, the threshold frequency is such that red is below the threshold frequency. Nothing's ever going to happen, no matter what, as long as I stay under the threshold frequency. But as soon as I go above the threshold frequency, there's a couple of things that you got to remember here. Number one, that is that it's always a 1-to-1 ratio above the threshold frequency. 1 photon will cause 1 electron, 10 photons will cause 10 electrons. The second thing you got to remember is if you're way above the threshold frequency, then more frequency causes more energy of the photon, which causes more energy of the ejected electron. So higher frequency results in having higher EK, kinetic energy of the electron. Therefore, more speed. The electron is going to be moving faster. Make sense? Okay, so you learned yesterday there was a few equations that we use here in this whole concept as well. The first one, we learned this the other day, actually, when I was here on Monday. E is equal to HF equals hc over lambda. Now, that's an equation that is not unique to the photoelectric effect. Okay, that's an equation that's valid anytime we have a photon, in any context, including the photoelectric effect. So, although it's valid outside of the photoelectric effect, you're still allowed to use it within the photoelectric effect. We also learned that W is equal to HF0 equals HC over lambda max. W is what we call the work function. W is we define it in two ways: the minimum energy necessary to eject an electron, or we could also think of it as the energy that's used up in the process of ejecting the electron. You think about that. W is energy. Energy is H times F. Minimum energy is H times minimum frequency. So we said a while ago when we were looking at these pictures, we said, this is the frequency that we have. This is the frequency that we need, right? This equation is what we have. This equation relates to what we need. We have this frequency. We have this wavelength. We have this energy. We need this frequency. We need this wavelength. We need this energy in order to cause electrons to be ejected. Okay, the first one, have, this is what we got. Second one, this is what we need in order to cause the electrons to be ejected. There's another equation. This one we starred yesterday because it's not on your data sheet. HF is equal to EK plus W, the work function. I'll star it again. It's not on your data sheet. I don't know why they don't put it on your data sheet. They used to, then they took it off. Maybe because they want you to know where it comes from, and they want you to be able to basically figure it out. This comes from the law of conservation of energy. HF, this is the energy that we start with, right? EI. HF is the energy of the photon. What starts this whole process? The photon, light. Photon strikes a metal, and electrons eject it sometimes. The initial energy is the energy of that photon. What do we end up with? Well, it's the electron that's ejected, right? That's the final energy, the kinetic energy of the ejected electron. Except that EI is not equal to EF here because we use up energy in the process. How much do we use up? The work function. The minimum energy necessary to eject the electron, the energy that's used up. So we're going to say EI is equal to the energy we start with is equal to the final energy plus whatever we used up in the process. If we start it with 10 and we end up with 8, how much did we use up in the process? 2. So the energy that we start with equal to the energy that we end with plus whatever we used up in the process of ejecting that electron, which in that case is 2. Now there is one more equation. You're going to have to just trust me on this equation for now. A little bit later on today, we'll give you some more detail on why you would do this. But understand that sometimes once an electron has been ejected, sometimes after this has happened, after everything you see up on the board has taken place, sometimes we might want to stop an electron. Like we want an electron that's already been ejected to stop moving away from the metal. Why would we want to do that? We'll deal with that a little bit later. Trust me for now. Sometimes we would want to stop it. If we stop it, we could analyze it using this. EK is, of course, EK of that electron is 1/2 mv squared, right? This would mean the initial energy. This would be the energy that the electron has after it's been ejected. And then when we stop it, what kind of energy do we have after the electron has been stopped? Well, car goes up a hill. We're stopping an electron again. Look over here on our always list. Charged particle accelerates in an electric field. EI equals EF. Car goes up a hill. What kind of energy does the car have at the bottom of the hill? Kinetic. What kind does it get converted to as it goes up the hill? Potential. So we would say that as this car slows down, it's a conversion of kinetic to potential. As this electron slows down and stops, it's a conversion of kinetic to potential. We're going to say 1/2 mv squared equals QV stop. V stop being the potential difference that is required to stop the hill. It'd be like the height of the hill required to stop the car. Does it make sense? If I said, how much hill is required to stop the car? You would say 1/2 mv squared equals mgh, and you solve for h. If I said what potential difference is required to stop the electron, you'd say, oh, 1/2 mv squared equals qv stop, and solve for v stop. Again, trust me on that now as to why you would ever want to do that. That'll come in a fairly short time here. Okay, what I do want to do right now, before we go over what the explanation of that in more detail, is to take a look at the fourth example, the one that you didn't have a chance to do yesterday. We'll go over that one now. It's on page 4 of the handout that I gave you on the first day of the unit. And then we'll give you a few minutes to work on some questions. Example number 4 says the wavelength of EMR incident on a photoelectric surface is 5 times 10 to the minus 7 meters. So we're saying here that a photoelectric surface is a material that will potentially emit electrons. Here's the wavelength that you shine on it. What's the maximum speed of the photoelectron? The photoelectron is just like any other electron, except it's not orbiting around the nucleus. It's been ejected. So don't think, oh, I need a new charge or a new mass. No, you don't. It's the same charge, same mass. It's just not orbiting. It's an ejected electron. Work function is 0.50 eV. Okay, what do we got here? The wavelength is 5.0 times 10 to the minus 7. I'm going to write down a couple things here just to refresh your memory. Remember, this one's what we have, right? This one's what we need to cause an electron to be ejected, right? This lambda here, is that lambda or is that lambda max? Is that what we have or what we need? That's what we got. That's what we have, right? So that's lambda, not lambda max. Sometimes you may be given a question with lambda max, the maximum wavelength, or sometimes we call it the threshold wavelength, like the threshold frequency. What's the maximum speed? We're looking for v here, not big V, little v. The work function is 0.50 eV. Okay? I think that's relatively straightforward that that's work function. Work function is what we need, right? What we need, not what we have. There's a number of equations that we know we can use here. See them up on the right side of the board there. What I didn't mention in the podcast that you watched yesterday, that I will mention today, is that if you're having trouble figuring out which equation to use, you probably want to try this one. Doesn't mean that's the one that's always going to work, but if you're having trouble figuring out which one to use, it's probably going to end up being that one. So give that one a try. We're going to say HF is equal to EK plus W. Oh, but I don't know, is that going to work? What are we going to do? What are we going to do to make that work? Sorry? Yes, that's exactly what we do. We replace HF with HC over lambda. EK, I don't have that either. Yeah, we'll replace it with 1/2 mv squared. This is why this equation ends up working so often for the trickier questions, is because there's so many substitutions that end up going into the mix there. It's not always immediately visible which equation to use. This is the one that allows the most substitutions and therefore gives you the most flexibility. Plus W. Okay, what do you want to use for Planck's constant here? The 4.14 eV or the 6.63 joules? EV. Makes sense to use EV here, right? Because I've got 0.5 EV. It doesn't work this time. Remember this, okay? If you can use whatever you want, EV or joules, for any equation, unless you're introducing this or this. If you're using either of those in the mix, you've got to use joules. So if you weren't looking for V, if you were just looking for EK, you could use EV, because you haven't used 1/2 mv squared or QV stop. But if you're looking for speed, and because of that you have to sub in 1/2 mv squared, then all of a sudden you must use joules now. Got it? Now, I know that when you're working on questions, people are going to ask me questions. They're going to get confused between EV and joules. I'll answer those questions. This is what I would do. This is what I would do in this situation. This is what I do in that situation. If you ask me tomorrow whether I should use EV or joules, guess what my answer is going to be? Joules. I'm just going to say joules. Use joules. The reason I'm going to say that tomorrow is because this. Like, you know, there are some times when you have to use, when you can use either one. Most times, in fact, you can use either one. There's a few situations where you can just use joules, not EV. If you're still confused tomorrow as to which one is which, then I'm going to suggest to you that you just use joules. Joules always works. EV usually works. If you're confused today, I'll help you. If you're confused tomorrow, I'll help you as well. But I'll say that, well, if you're still confused the second day, just take the easier way and always use joules, even though it does require a little bit more work sometimes. Okay, so we do have to use joules here, no question. That means we're going to use the Planck's constants at 6.63. C is 3 times 10 to the 8 over 5 times 10 to the minus 7. It's an ejected electron, but it still has a mass of 9.11 times 10 to the minus 31. And, 0.5 EVs. You guys remember how to do that conversion? 1 EV is 1.6 times 10 to the minus 19 coulombs. 0.5 EV is X. X is 8 times 10 to the minus 20 joules. Remember that? Did that back in Unit 2 a few times. So if we hadn't have had the 1/2 mv squared, we could have stuck with EV. As soon as we introduced 1/2 mv squared, we had to use joules. If you're confused, just use joules always. Okay, we get this side, this left side, it gives us 3.978 times 10 to the negative 19. Let's take this over by subtracting. Then let's multiply it by 2, divide by 9.11, and then let's square root it. And we get a speed that's 8.4 times 10 to the 5 meters per second. Is that a reasonable speed? Remember what we usually get for charged particles? 10 to the 5, 10 to the 6. Yeah, that's right in that range that we usually expect to see. Could be slower, could be faster, but usually it's somewhere in that 10 to the 5, 10 to the 6. Okay, make sense? Couple things, right? You write down your givens. You think about as you write down your givens, especially for wavelength and frequency, is this what I have or is this what I need? Is this F or F0, lambda or lambda max? Okay, and then the second thing you think is, if I have any confusion over which equation to use, like if you know which equation to use, go with it. If you're confused about which one to try, then try this one. And thirdly, remember that you can always use joules, but you don't always have to use joules. Okay, do whatever you want, unless you introduce 1/2 mv squared or QV stop, then you got to use joules. Confused about that? Just convert to joules always and do your thing. What I'd get to work on right now is worksheet number 20. You did questions 1 and 2 already, so I'm going to ask you to do now questions 3, well, the rest of the worksheet. Questions 3 through, you know, we'll stop you at 13. Questions 3 through 13, which is a couple of questions off the worksheet. Give you some time to work on those now in class. I want to do 2 of these questions now. Specifically, I want to do questions 6 and 8, but I want to relate 5 and 6 together just briefly, even though I don't want to solve both of them. Question 6, you can see here, there was a typo, 5.5 times 10 to the 7 meters. Should have been a wavelength of 5.5 times 10 to the negative 7 meters. As I relate these two together, let me draw a little table on the side here. Okay, let's say we got F and we've got lambda. We know that F and lambda are inversely related to each other, right? So as one goes up, the other one goes down. Let's say the frequency is 1, 2, 3, 4, 5. The wavelength, let's say, is 10, 9, 8, 7, 6. These numbers wouldn't actually work, but you get the idea that it's an inverse relationship, right? Let's say the threshold frequency is 3. Okay, that means if we have a frequency of 2, electrons will not be ejected because we're not above the threshold frequency. If we have a frequency of 4, then electrons will be ejected because we're above the threshold frequency, right? That threshold frequency of 3 corresponds to a lambda of 8. So we would say our threshold wavelength, or our lambda max, is 8. We need to be above 3 for frequency to cause the electrons to be ejected. We need to be blank 8 to cause the electrons to be ejected. Above 3 or below 8. Look, 4 causes the electrons to be ejected, but 4 corresponds to a wavelength of 7, which is below 8. So you need to be above the threshold frequency to cause the electrons to be ejected. You need the wavelength to be below the threshold wavelength in order for electrons to be ejected. Does that make sense? The higher the frequency, the better. The lower the wavelength, the better, if you're trying to cause the electrons to be ejected. So in question number 5, actually, we'll do number 6, and then we'll just relate that to number 5. 6 says the work function of a particular metal is 2.5 eV. Will that cause electrons to be ejected? We got a couple of options here. We'll do it both ways. First way, I'm going to say the energy that we have is h times c over lambda. hc over lambda. If I multiply h times c over lambda, and I'd do that if I could find my calculator. When I do this, I get an energy of 2.26 eV. Remember what I said, guys, earlier? This is what I have. This is what I need. Is what I have bigger than what I need? No. So electrons will not be ejected there, right? Now, the other way to tackle this, and I saw a couple of people tackling it this way, just as good as the way that I just did it, people said, well, if this is the work function, we could calculate the threshold frequency. W is equal to h times F0. F0 is W over h. And when I solve for that, I get a threshold frequency of, sorry, I don't want to use this. I want to use, that's what I'd use in this question, right, because I have frequency. This one I'd say W is equal to hc over lambda max. I'd say lambda max is equal to, solve that, works out to be 4.968 times 10 to the minus 7 meters. Remember what we need to be below the threshold wavelength. Is the wavelength below this? Is what I have below what I need? Is what I have, 5.5, under what I need? 4.9? Are we below the threshold wavelength? No. So electrons would not be ejected. So look at it either way. I don't care. Find the energy of the photon compared to the work function, or take your work function, find your threshold wavelength, and then compare your wavelength to the threshold wavelength. Either way works. The other question I want to go over is number 8, which says, calculate the maximum kinetic energy of electrons emitted from a metal whose work function is 1.5 eV, visible light 700 nanometers. This is what I need. This is what I need. What is this? 700 nanometers. Is this what I have or what I need? Yeah, like it's illuminated with this light. I don't know what I need for a wavelength. This is what I got. We want to find EK, right? Now notice we often say maximum kinetic energy. Like last couple of days I've been saying kinetic energy. Sometimes the questions say maximum. It truly is maximum. Because when we solve for EK, that doesn't mean all the electrons have that much kinetic energy. That's the most that they can have. If you see the term maximum, that's okay. Understand it's the same thing as we've been talking about it. It's a more accurate way, actually, of talking about it than the way that we have been. Not sure which one to use? I'll just go with this one, the one that's not on my data sheet. Let's replace HF with HC over lambda. Now, I've got W in EV. Can I stick with EV, or do I have to use joules? Can I use joules? Always. Do I have to use joules? No, I don't have to here. I've got EK, but that's not 1/2 mv squared or QV. If I use 1/2 mv squared or QV, I've got to use joules. If I'm just using EK, that's fine. If you want to convert to joules, though, go ahead and do that. Okay, I'm going to use the 4.14 value and stick with the electron volts. Lambda is 700 times 10 to the minus 9. So calculate this number on the left side. Take the 1.5 over by subtracting, and that's going to give me EK. The answer that I get in electron volts is 0.278 EVs. If you weren't comfortable with EVs and you're one of those people that just always want to use joules, that's fine. Then you would have gotten an answer in joules, and it would have been 4.41 times 10 to the minus 20 joules. So either one of those would have worked. How many people finished up to number 8? Okay, how many people got 0.278 EV? Okay, how many people got 4.41 times 10 to the minus 20 joules? Okay, about half and half. Just be aware that on a test, like they're going to specify which unit to use, right? You can still do it in joules. You just may have to convert it back to electron volts at the end, that's all. Let's quickly do 7 as well. Let's quickly set up 7, okay? Stopping voltage, electron has this speed. This is just, remember we said EK is equal to 1/2 mv squared, but it's also equal to QV stop. So you get the mass of the electron, you get the speed of the electron, you get the charge of the electron. You're going to find the stopping voltage or the stopping potential there. Does that make sense, Carly? This diagram represents an experiment that might be performed where we would want to stop the electron dead in its tracks. Remember we said a little while ago, you're going to have to just trust me on this, why we would want to stop an electron dead in its tracks. Well, let's look at this, the setup of this, and let's get some results from this, and then let's see from those results where they would take us. What would be the purpose of doing an experiment where we'd want to stop electrons? Just bear with me for a second, though, here, before we get to that point. You can see that this collector here is charged positive, and this one is charged negative. That means that this power supply must have two terminals, a positive and a negative, like this. These photons up here that are incident on this electron-emitting metal surface, they must have a frequency that is greater than the threshold frequency. What we have, what we need. Why are we saying what we have is greater than what we need? Because the electrons are being ejected. F has got to be bigger than F0. Lambda would be smaller than lambda max. E would be bigger than W, because what we have is more than what we need. Now, these electrons get ejected. They get attracted to this positive collector plate, this plate that is charged positive because of this power supply. And as a result of that, they're going to move over here. In fact, they're going to move over here, and electrons are going to continue moving around this circuit here. This ammeter that you see at the bottom is a device that's used to measure electric current. So as electrons are scooting by that, like this, counterclockwise here, this ammeter will have a reading. It'll read something. There's a current flowing through this ammeter because electrons are moving around this circuit, because even though there's a gap here, even though there's a gap right here, we have these electrons being ejected and being attracted toward this positively charged plate. There's an electric current. Okay, we haven't really done anything yet other than kind of set this up. Now, imagine what would happen if we reversed the polarity of the power supply. Imagine what would happen if we took this power supply and made this the negative terminal and this the positive terminal. That makes this collector negative and makes this one positive. Our photons still have a frequency that are greater than the threshold frequency. What we have is bigger than what we need. So electrons are still ejected. But now the electrons are being repelled by this collector, right? This collector over here. Now this is like the car going up the hill. How much height of a hill is required to stop the car? How much potential difference is required to stop the electron? So here's what we're going to do. We're going to turn up the power supply, increase it, increase it, increase it, increase it, until we stop the electron. Record the value of the frequency of EMR that you were using. Record the stopping potential that was required to stop that electron. Increase the frequency a little bit. See what stopping potential is again. Increase the frequency more. Increase the potential difference to see what the value is that's required to stop the electron. Got it? Now, how do you know when the electron is stopped? Can't see it. How do you know when the electron has stopped moving and the electrons are no longer moving toward the collector? The ammeter reads 0. There's no current going through there anymore, right? So that's our measure of the stopped electrons. Now, this is our data table. We recorded, we manipulated the frequency. Responding to that was the potential difference required to stop the electron. We turned that into an analysis table. Frequency again, and then the corresponding EK max. We'd simply find that by multiplying Q times the stopping potential that we got over here. Now, what do you think you're going to do with this? If this was a real lab, what would you do with this? You'd plot a graph. EK would appear on the y-axis, EP would appear, and the frequency would appear on the x-axis. You've got this graph photocopied for you. Don't worry about copying down the data. I'll assume that you could plot the graph from the data, right? Look at the units here. Pay attention to that, because if you were doing a calculation, you'd need those units in there, right? 10 to the minus 18, 10 to the positive 15. Notice the shape of the graph I get. It's a straight line. Notice as well that if I extend this line and extend this line, there is a y-intercept. Most of the ones we do don't have a y-intercept, right? Right? All right. How would we deal with this? How would we deal with this? Before we get there, how do we deal with any straight line graph? Y equals mx plus b. What's the y-axis here? That would be EK. M is, what's M? Slope. What's x? Hertz or frequency. There is a y-intercept here, right? There's clearly a y-intercept there, so we can't get rid of that. What equation on your data sheet has EK and F? Not E and F, but EK and F. Either on your data sheet or one that you've got to come up with on your own. Which one, Carly? No, EK doesn't equal HF. The photon energy equals HF. EK doesn't equal HF. Yeah. We're going to say HF is equal to EK plus W. Now, rearrange this one to solve for, what variable do you want to solve for here? Quick. EK. I get EK, when I rearrange it, equal to HF minus W. Cross off EK because it appears in both. Cross off F because it appears in both. What are we left with? Slope is equal to H. The slope of this graph is equal to Planck's constant. So why would we want to stop an electron? Maybe we want to find Planck's constant. What would the y-intercept be equal to? Negative W. Maybe we want to find the work function. This would be, well, let's say, -5. What would the work function be? 5. if b is equal to negative, or if the work function is negative b, then the work function will be negative 5 or 5. Now, sometimes it's difficult to extrapolate a graph and see what the y-intercept is, just because of the geography of your paper, right? It's sometimes, you know, you don't have the graph paper below it, you got a question below it, whatever. There's another way to find the work function here. We could also say work function is equal to Planck's constant times the threshold frequency. Planck's constant is the slope. Last thing that I want to do with you today. Where do you think you're going to get the threshold frequency from this graph? What is it? The x-intercept. Think about that. Down here, when the kinetic energy is negative, that doesn't really mean anything, right? Like kinetic energy is negative, the electron has not been ejected. This is where the kinetic energy begins to be positive. This is where the electron has been ejected. This is the frequency at which electrons are ejected. So there's basically three things that you get from this graph. Planck's constant, the threshold frequency, or the work function. You can get the work function by saying h times the threshold frequency, the slope times the x-intercept, or you can get it by taking the y-intercept, whatever ends up being most convenient for you. You should get the same answer. Good? Like this? You know what, the reason that I go over this graph specifically, we don't usually go over specific graphs in class. When we do a lab, we do, right? But not so much in class. The reason I go over this one specifically is because it's not uncommon to see this one specifically on a test or on an exam. Okay, I'm not trying to throw you a hint as it, you know, for your specific test next Wednesday, but it's not uncommon to see it at some point. There's a million different graphs we could see. If there's one that we see relatively often, we might as well spend some time on that, right? Okay. In the end, even if we didn't, you guys could have figured this out, but if we see it often, why not just go over it together? Your homework for tonight is to finish worksheet number 20 up to number 13. Now, lots of you are well on your way towards that. I also want you to do practice question set number 25 that I posted on Google Classroom this morning.